In this video we use fundamental concepts in nuclear chemistry to begin to explain what fission and fusion are. Alright, in a prior video we have studied the thermodynamic stability of nuclei, and then what we've said is that when you examine nuclei across the periodic table and isotopes of those elements, you can map here the binding energy of the protons and neutrons in that nucleus, and then see which one of these nuclei are more stable. This mass number A, and when you find this a plot that looks like this. Alright, so here you have the most stable nucleus known, which is iron 56. And then here you have high mass number nuclei, such as uranium, for example uranium-235. And here you will have the lowest mass number nuclei that we know, for example proton. Okay, now so the idea here is that the most stable nucleus is iron 56, right? So this is not so stable, and that is not so stable. So here's an opportunity for you to transform nuclei and then gain energy as a consequence of that process. For example, you might imagine how you can transform this uranium-235 into a more stable nuclei, and you can be climbing this ladder all the way to iron 56, and all that should generate energy because you're going from a not so stable set of nuclei to the more stable nucleus. The same thing happens here with in this part of the periodic table, right? What you have is that, well, you can sort of try to generate nuclei of increasing mass, okay, in order to generate ever stable nuclei until you get to iron 56. Okay, so the idea here is that the process whereby you climb the ladder this way, that is called fission, and the processes whether you go from less stable nuclei to more stable nuclei, this side of the ladder, that is what we call fusion. All right, so we're going to study each one of those processes in turn. Fission is the most common one, that is the one that is used in nuclear power stations, and the idea is that you're going to get a massive nucleus and then break it apart into less massive parts, and again, if those less massive parts are actually more stable than the nucleus that you started with, then there's going to be a lot of energy released. Okay, so one such example would be the reaction of uranium-235, which is a very common fuel in nuclear stations, with a neutron. So it has a mass number but no atomic number. And that cracks this uranium atom into a smaller nuclei. Okay, so one of the chemical reactions that can take place here is this is going to be barium 141, and then also you generate krypton 92. With the production of 3 neutrons, and that is important. Neutrons. Okay, so again, what you're generating here is you're taking a nucleus that is not particularly stable, and then through a chemical process, you break it into nuclei that will be a little more stable, right? So overall, this actually releases a huge amount of energy. The delta E for that particular process is minus 2.1, 10 to the 10 kilojoules per mole. Again, this type of energy is 10 to the 10 kilojoules per mole. Those dwarf any energy that we actually have in chemical reactions in which you're simply rearranging atoms, right? The energies of those chemical reactions are in the few kilojoules to maybe 100 or 1,000 kilojoules per mole, right? So these are millions of times on a per mole basis more energetic than any chemical transformation, right? So there's a lot of interest in trying to harness these processes for energy production. Now, something that is important about this fusion process that we actually have written here, so this is fission process. Okay, one of the important things about this fission process is that you generate more neutrons in products than you require in reagents. And that is interesting because if there's more uranium-235 around, then these neutrons that you have generated anew are going to be able to undergo fission with that uranium, right? So this is a self-sustaining type of reaction, is what we call a chain reaction, right? If your reaction produces more reagents, okay, then if you find the other type of reagent, then you can continue to propagate this process. Okay, so part of the worries about nuclear stations is, well, how do we begin to control the amount of neutrons that you're producing and how they mix with more fissionable material, so that you actually don't have runaway processes that can be dangerous. Okay, so this is the process of fission, again, where you're trying to generate ever stable nuclei from more unstable nuclei, and then try to harness that energy in order to generate electricity. All right, so this is much better developed, and it has been used in military applications, of course, and in energy generation. The one that is not so common, at least on Earth, is the process of fusion, in which you take lighter nuclei and then try to bring them together to generate heavier nuclei that are more stable. And again, as long as you're going up here this ladder, that is going to generate a lot of energy. All right, so let's review this process of fusion as opposed to fission, which is what we have right here. All right, so typical processes in fusion would be something like this. You get one proton and then collide it with another proton to generate, or a hydrogen atom with another hydrogen atom to generate an atom of deuterium, which is this isotope, and this carries the generation of a positron. Okay, and then what you can get is take that deuterium atom and then make it react with another deuterium atom, and this can generate now a helium atom 3. Okay, or with a proton in this case. That's how the reaction would be. All right, so again, notice that in these reactions, what you're actually doing is you continue to increase the mass number, the number of protons, so you're climbing up the ladder, and again, this should be quite energetic. There is a problem with these processes, and that is, of course, that here you actually need to bring together two particles that have positive charge, right? Notice that this is a +1 charge, that is a +1 charge, and of course it's very, very difficult to bring two particles that have the same charge together so that they react to generate a new nucleus. The barrier for these processes is extraordinarily high, and that means that on Earth this can only be carried out if you actually put in a lot of energy, like make these particles, accelerate them, and then make them collide at very, very high energy so that they can pass that barrier and then form these new nuclei. Or you can use lasers to provide that energy in a different way. But either way, this is actually very expensive, and we don't know how to do this reliably yet. Okay, people are thinking about cold fusion processes in which you don't need so much energy input, but that's still under development. Of course, the place where where these reactions happen continuously is the surface of the sun, or in the sun, right? So in the sun, you sufficiently have enough energy to be able to produce this type of fusion processes. All right, so in this video we have introduced the concepts of fission and fusion and as ways to generate energy for applications. Okay, we've seen that fission is something that we normally do in nuclear power stations and in military applications. Fusion is something that is only experimental at this point, even though it does exist in nature, particularly in the sun.